Good afternoon, everyone. I would like to give an overview of what's going to come this week, and on Monday we are going to work on this subject, and I would like you to review that. I will spend probably 1/3 of the class doing problems with force, which we worked last week, and this week we are going to be focusing on chapter 5, which goes over the concept of energy. So the first concept here to be considered is the concept of work. So work is the product of a force times displacement. The unit of work is called energy, joules. Work is a scalar, meaning the product of a force per displacement. When you convert that to a scalar quantity, is F displacement cosine of the angle between those two. This is right here. It's right here. So here's an example. You have a bucket of water, and then looking at the bucket itself, what are the forces on it? So you have a weight, a downward gravity force, and you have an upward force that is exerted on the bucket by the person's hand. So if the bucket's not moving up or down, if it remains at the same level, these two forces cancel out. So in this case, there is no work done if you move the bucket laterally to the right, in this case, without going up or down. You know what I mean? So you hold the bucket and just move to the side. There is no work done on the bucket, because the work done by the hand and by the gravity, they will cancel out. So there is no force applied in the direction of motion. There is no net force. Those two forces cancel out. No net force applied in the direction of motion. Okay. Now here are a few examples. Like, let's say you have a block and there is an upward force that is existing, but it can't overcome gravity. So the block's not really going up, right? And is being, let's say, supported by a table or something. So there is a gravity force there. So this force F doesn't do any work. So when the force happens to be perpendicular to the direction of motion, that force will not do any work. But here's an example where the force is being acted against the direction of motion, right? The block is moving to the right. So the work done by this force is a negative work. It's F times the displacement times cosine of the angle between those two, which is 180. Cosine of 180 is -1. This is a force doing a positive work, and this is a force doing a negative work. Again, it goes, when you project this force against the direction of motion, it gives you a negative work. And I know you keep thinking, what this work has to do with anything. Well, what one of the major outcomes of this concept of work is to introduce, will enable us to introduce the concept of energy, more particularly kinetic energy. So kinetic energy, we saw the definition of work, right? Is a net force times displacement as a vector and when you convert that to a number, is F times displacement times cosine of the angle between those two. Now, energy is a quantity that, as we're going to learn, it conserves if you can account for the entire energy of a system. So let's introduce kinetic energy. Kinetic energy has an expression: half of the mass times velocity square, or speed square. And this is one of the most robust theorems there is in physics, especially in mechanics, is that if you happen to be able to calculate the entire work done on a system by a set of forces, the total work done is going to be equal to the change in kinetic energy of that system, which is final kinetic energy. This is half mv squared kinetic energy, half kinetic energy, minus the initial kinetic energy. So this work is the net work, is the work done by all forces. So if you have problems in which you can identify the forces, as we did in class last week, first of all, and this body is moving from point A to point B, and you can determine what is the work done by each of the forces that you identify, and you add those quantities, so the final number is going to be equal to the change in kinetic energy. This is very robust because we allow you to do all sort of problems we are exploring in the class today. So kinetic energy, keep that in mind. Here an example. You have a driver with a car that has a given mass and is traveling with this velocity, 35 meters per second, and pressing the brake to avoid hitting a truck that is ahead of it. Okay. After the brakes are applied, a constant kinetic friction force of magnitude given acts on the car. So when you press the brake, now you have this blue arrow here. This is to indicate the kinetic friction. Remember, kinetic friction is a force that arises by the virtue of the contact between two surfaces, and since the surfaces are not smooth and they are at atomic level, you have always interaction, then there is some resistance that prevents motion to go freely. So the car moves to the right. There is a force applied to the left. So let's say, at what minimal distance should the brakes be applied to avoid collision with the other vehicle? So assume for now, so you want to find del x, right? And you want this car to move del x so that it stops before colliding with this car. So del x has to be some distance that, luckily for the driver, is big enough so that the car is able to stop right here. Stop means final velocity is what? 0. Correct? So if you think about kinetic energy, final kinetic energy is 0. Initial kinetic energy is given by half mass of the car and the initial velocity square. So you have the change in kinetic energy. So we want to find what is the displacement the car can have, the minimum one. Of course, I mean the maximum displacement, right? I'm sorry, the minimum displacement. So the maximum, you're going to crush yourself. So the force is given. It's right here. So you can get your displacement because this quantity is known. See how robust it is? That's how we do. Now friction is dissipated, friction is lost, and it's called a non-conservative energy. So if you have a system where non-conservative energy takes place, like friction, when you do your work, the total net work equals to kinetic energy, change in kinetic energy, you have to include also the work done by these forces that dissipates as the system moves. Gravitational potential energy. This energy is the one, when you hold something with your hand and you let it go, that thing falls. So you can think that by supporting something with your hand, by holding something with your hand, you have potential. If you let it go, you have some potential energy stored in there that can be converted into kinetic energy. The gravitational potential energy is given by this expression, mg del y, mgy, and mgy is the potential, gravitational potential energy of an object in respect to the ground. And the unit is joules, the unit of energy. Again, we are going to work on problems in the classroom Monday. So the so-called mechanical energy is when you can add together the kinetic energy and conservative forces like gravity to solve problems. And so let's try a review of concepts quickly, because that's the must we're going to see in class on Monday. And here it is. Make a little summary of concepts. There you go. So in this chapter we are tackling the concept of energy. Energy has a unity of joules, and the first concept we learn is the concept of work, represented by letter W, and that is equal to the dot product between force and displacement. So if you have a block that is being acted upon by a force F this way, that makes an angle, let's say 20 degrees with the horizontal, and the block moves to the right, X direction, then there is a work done on the block, which is F times whatever X that block moves times cosine of 20. And the unity of this is joule. Okay. So we also learn about kinetic energy. Kinetic energy, simply stating, is half mass of the object considering velocity square. Now, if we go back to the same example, we have a force F applied with an angle 20 degrees, and this block moves, let's make numbers, right? Let's make a force of 20 newtons, and let's think of our block, and I have to come up with an angle. Let's make this angle 60 degrees. So, and the block moves 2 meters to the right, and it starts moving with a velocity that is 0 meters per second. Okay? And let's say we want to find what is the velocity of the block at this point. we can apply the concept of work, net work, as being the change in kinetic energy of your system. What is the net work done in here? There is a normal force, there is a weight, but these two forces, they cancel out. Fg, I mean. So these two forces cancel out, so the net work is done by F times displacement times cosine of the angle between those two. This is equal change in kinetic energy half. Oh, my block, let's say, has a mass of 10 kilograms. M V final square minus half M V initial square. So let's say we want to find the final velocity. We don't know. Well, for a force of 20 newtons, the block moving 2 meters, cosine of 60 is half. The final velocity I want to find, and I know the initial velocity is 0, so this is 0, right? The block's not moving in the beginning right here. So this is equal to half, a mass is 10 grams. Velocity square is what I want to find. Cut 2. And then we find our final velocity as being 2 meters per second. See that? So it's some way of solving the problems we learned before that involves forces and acceleration, using a very robust technique, which is the work kinetic energy fielding, and using energy as a way to solve situations. If you have any mass, oops, this is not horizontal at all, is it? Man, doesn't look like. Okay. This is floor, and you have a block up here that has a mass of 1 kilogram, and the block is not moving because it's being held in place by some force. Let's say you are holding this, and then you let it go from v equals 0, and the block gets and smashed on the floor, right? Of course, when it's smashed the floor, it stops, but before it's touched the floor, it has some speed. Now, the potential energy, gravitational potential energy of this block we saw in the book is mgh, which is, in my case here, y. This energy, is gravitational potential energy, is also given in joules. So that this gravitational potential energy would be 1 times 9.8 times, for a height of 10 meters, times 10, 9.8 joules. Okay, so we are on Monday again solving problems in classroom, and I would like you to go with this cheat sheet. One is giving the definition of work, at least you saw it before. Second, kinetic energy. Gravitational potential energy. Always vertical displacement. And the work, net work, done on a system is equal to the change in kinetic energy of that system. Okay, so see you on Monday, and let's do a good work then. Don't forget to bring the online lab that I recommend you to do. That's going to be graded.